What's the date of the second one again? Is it tomorrow? Tomorrow, okay. Okay, got it. All right, thank you. Okay, while we're talking about campus activities, I'd like to tell you about an event coming up, Picnic with the Purdue Wets. It's free Sunday, September 13 at 6 p.m. on Slater Hill. These Purdue Wets are wonderful singers. They put on great shows, and this is free. So check them out. They are really awesome. Once again, that's Sunday, September 13 at 6. Okay, now let's do math. Oh, I forgot to say good morning. Thank you. How was your long weekend? Good? Outstanding? Good. Alrighty, so let's continue with Chapter 6. Today we're going to look at 6.3. We'll look at how we can calculate volumes by using a different method than the one we saw last time. And this method is called cylindrical shells. So quick recap. Last time we looked at calculating volumes by using disk or washer. And the way we did that, remember, I'll use a cone as an example again, is we set up a bunch of disks. Inside the cone, in this example, and then we allow the disks to shrink to almost zero thickness and letting the number of disks go to infinity. Today we're going to look at the same goal here. The goal is still to calculate the volume, but the method that we go about is different. And let me use the cone example again. And I'll use the same cone we saw last Friday. All right, so the region is bounded by that line at the top. By the two coordinate axes. And we're rotating this to go about the y-axis. So notice what happens if I set up a rectangle that's parallel to the axis of revolution this time. First of all, when we rotate this, we know we're going to get a cone out of it. So here's the end product. Last time with the disk and washer method, remember the rectangle was perpendicular to the axis of revolution. This time we're going to make them parallel to the axis of revolution. And watch when we spin this rectangle around the y-axis. When you do that, this rectangle turns out to look something like this. Right? It's a hollow shell, hollow cylinder. Can you visualize that? Yep. Okay. When we spin this around, we get a hollow shell inside. And that's one part of the cone. Then what we do is we take another rectangle somewhere else, over here, for example. Then we spin that around again. And this time we're going to get a shorter but wider cylinder. Right? You see that? And then a rectangle near here, spin that around, it's going to become a very tall but very skinny cylinder. Okay, so then we just start stacking these cylinders one inside another. Start with the widest one, and then slightly slimmer one, but taller, and we keep stacking them. One inside another. It's like those Russian dolls, right? You open one up, you get a smaller one. Open up another one, you get a smaller one. And it keeps going. Exactly the same idea here. Okay, so there's the basic idea here. Makes sense before we dissect the mathematics behind it? Yep? Okay. Now let's see how we can calculate the volume this way. The fundamental idea is the same. We need to calculate the volume of one shell. If we can calculate one shell, then the integration will add up all the shells we want. So let's see how that works. Let me resketch the partial cone here, just a part of it. The y-axis is coming out here. Now we need a volume of this thing. There are several ways to calculate volume of this cylindrical shell. I'll show you one way that I think is intuitively the most clear way to do that. We're going to make a cut. So let's make a cut, let's say, straight down the middle here. And then I'm going to unwrap that thing. And what do I get when I unwrap it? I get a rectangular slab, right? It looks something like this. I'll exaggerate the thickness here, just so we can really see what we're dealing with. Okay, so we take this, take a cut, and then unwrap this thing. we know how to calculate the volume of this thing. We know the thickness of that rectangle we started with was dx. And that's going to become the thickness here. And then this height obviously comes from the height of the rectangle, right? What about the length? How long is this rectangle? Geometrically, what is this length? Good. This length here is the circumference of the cylinder, right? The cross-sectional cylinder. So that's the circumference. Now, how do you calculate the circumference of a circle? 2 pi times the radius. All right, so the radius comes from here. Right, the radius is from the axis of revolution to either the inside or the outside of the shell. We don't really care whether it's inside or outside, because in the end, we're going to shrink dx to almost 0. So the distinction between inside and outside is totally irrelevant at the end. So let's just, for simplicity, say it is from the axis of revolution to the outside of the shell, which, if you look at where it came from, that's right here. This is the radius. The radius is measured from the rectangle to the axis of revolution. Does that make sense? How we calculate this, the volume of that slab? Yes? Good. Okay, so that's one slab. See, just like with the disk method, if you can calculate the volume of one of these guys, you let integration take care of the rest. So the key is just one. So here is the key thing we need to remember. Volume of one shell is equal to 2 pi times the radius times the height times the thickness. Okay, let's look at our cone example here. The line at the top. This is 2. 2 minus x. And here's some arbitrary rectangle that turns into a shell. Let's find out what this looks like. We have our 2 pi. The first thing we encounter is the radius. Radius, remember, is the radius from the center, from the axis of revolution to the rectangle, because that's how we get our hoop out of it. So how would you express the radius in this example? X, good. And why is it x? Yeah, that's the distance from, so here is x is equal to 0. and I'm putting the rectangle at some arbitrary x of my choice. So obviously, between 0 and x, we have a distance of x. Make sense? Good? Good with the radius? So that's x. Height of rectangle, what would that be? Yeah, top minus bottom, so 2 minus x. Thickness, dx, yep. So that's one shell. And we want a whole bunch of these shells. Now we integrate. Entire cone. So where do we integrate from? 0 to 2, good. From 0, left of the region, we're integrating in x. So we start at the left, end at 2, and then 2 pi x times 2 minus x dx. And now the easy part. Let's take 2 pi out of here and distribute the x into here. All right? And trust me, this turns out to be 8 pi over 3. Okay, and then if you look back in your notes, that's exactly the same volume we calculated on Friday using the disk or the wash disk method. Because it's the same shape. We have to get the same volume no matter how we dissect the thing. So the key is right here, right? If we can figure out the volume of one shell, then you're set. Integration will take care of the rest. Any question on this, on the work I've shown here? Okay, let's do a few more. More interesting stuff. That cone is cool, but let's do some other stuff. All right, so the region is bounded by y is e to the minus x, y equal to 0, x is equal to 2, and we're taking this to go about the y-axis again. Okay, so y is e to the minus x, 0, 2 for x, and then going around the y-axis. Once again, a basic sketch. All right, so you need to know the basic shape of exponential graphs. If this is positive, then we know it starts low and ends up high. But if the exponent is negative, then it gets reversed. It starts high and uses the x-axis as a horizontal asymptote. Never quite get there, but awfully close after a while. What's the y-intercept? 1. Good, because e to the 0 is 1. Excellent. Okay, so now we got this curve here, and we're bounding the left by y equal to, I think I'm missing something, x is equal to 0. So we want to bound left by x is equal to 0. So this guy right here. We bound below by this. And bound on the top by making it bad. Good enough. And then bounding the right by x is equal to 2. Let's say x is equal to 2 is right here. Okay, so now we got this shape here. It's not quite a trapezoid because it's curved on the top, but something kind of like that. Now we're taking this to go around the y-axis. Okay, now visualize and describe the final product we get out of this after we do the revolution. What do we get? See, I don't know what to call this. I'm trying to see if you know what to call this shape. Kind of a mountain, okay. Yeah, that's not a bad description. It has a round base. Of course. Yep, good. So I'm teaching math because I can't draw. So forgive me. Is that good? Yeah, something like that. Okay, so that's the thing we're trying to calculate the volume of, right? Just like the last example, set up one shell and then let integration take care of the rest. Key thing to remember, when you use the shell method, the rectangle you draw is always parallel to the axis of revolution. In the disk washer method, we will set up a rectangle that's perpendicular to that. That's how we get a disk. Here, you swing this thing around that's perpendicular to it, and we get our shell out of it. Volume of one shell. Formula on the last page. 2 pi radius, height, and then thickness. One step at a time. 2 pi. Radius. What's the radius? Good. Measure from revolution axis to your rectangle. From here to here, that's x. Because the rectangle forms the outer wall of the cylindrical shell. So x. So that's my radius. Height. E to the minus x, right. Right? That's determined by the top curve minus the bottom curve, which is 0. So here's the height. Thickness, dx. Oh, hold on. Go back up one. This should be e to the x squared. Okay, that made a huge difference. Don't worry about that difference that would have made, but let's just focus on what we're supposed to do. This is better now, okay? I miss out the x. Okay, does that change the shape? Does that change the fundamental shape of that curve I drew on the top? It's still the same shape, but the height has been changed somewhat, right? So, the height of our little hat here is a little bit different, but the shape remains the same. This curve is still the shape of e to the minus x squared. It still crosses the y-axis at 1. Okay, so here we go. We got our radius, we got our height, right? That's one shell. Now we calculate the volume of the entire thing. Integrate. From where to where? Good. 0 to 2, left to right, right? 2 pi x e to the minus x squared dx. All right, now remember how to integrate this? Substitution. Yes, you use substitution. Good. What should u be? X squared? Is that what I heard? Negative x squared? Sure. Okay. And then what? du is minus 2x dx. Good. All right, so let's see what this turned into. Let's leave the pi out here. And here's my 2x e to the minus x squared. I'm just regrouping things a little bit. So this guy turns into a u. That's our definition of u. And then 2x dx together turns into what? Negative du. Good. Right? 2x dx. If I had a minus sign in front, I get du, but I'm missing that. So 2x dx turns into minus 2x du. Let's adjust our integration limits too. So the upper limit used to be x is equal to 2. When we go to u, it becomes negative 4. Good. The lower limit used to be x is equal to 0. When we go to u, it remained at 0. You remember the u substitution, right? Yes? No? Yes? No? Well, you better. Okay, if you're rusty with the u substitution, make sure you at least review a little bit about how this thing is done. If you have trouble, come see me in my office. I'll help you out. Yeah. What do you mean? Okay, and there are two ways to do this. One is to integrate that and go back to x and use the old limits. The other way is to finish the entire integration in u and never go back to x. And if you do the second way, which is the way I'm going to do, you need to make sure the limits used to refer to x. Right? X went from 0 to 2, but we're changing this whole thing to be u now. So the old limits refer to x don't apply to u the way it used to apply to x. So we're going to reflect that change. All right, so let's see what my integral turned out. What does it turn into? 0 to minus 4 take the pi out there. Minus pi, yep, let's take a minus pi out there. Minus 4. Okay, did I catch all the signs? All right, so what's inside here then? E to the u du, good. What's the integral of e to the u? Minus. All right. Minus pi e to the minus 4 minus pi e to the 0. So what do we get? We get pi minus 1 over e to the 4. I'm missing a pi here. Take the pi out. We get this. Question? Okay, the pi became negative because in the previous step here, I had a minus du here. So it's minus 1 times the du. So I gave the minus to pi, and then I pulled it out. You could have kept it inside, that's fine. But, since we're always pulling out constants, I figured let's take the negative sign with it. Okay, questions on this example? Yes? If I had taken a negative pi, but I did. Okay. All right, everyone else okay with this then? Yeah, gotta keep track of your minus sign. You see how easily I screw that thing up. But that's the right answer here. Okay, let's do something more interesting. This time the region is bounded by x is equal to 1 plus y minus 2, the quantity squared, and x is equal to 5. And we're taking this to go about the x-axis. And by now, you can probably predict that if you see an equation expressed as a function, x as a function of y, we're going to end up integrating in what? Y instead of x, right? That's often the case. Then we'll see what happens. Because we're kind of dictated by setting up the rectangle parallel to the axis of revolution. So that dictates what variable we integrate in. Let's get a sketch out of this. What shape is this? Excellent. Parabola, which way does it open? To the right. Good. Where is the vertex of the parabola? At 2, 1. Okay, good. Excellent. So here's how you can figure this out. When y is equal to 2, if y is equal to 2, x is equal to 1, right? So here's 1 point. The smallest x can ever be is 1. because this thing is always positive because it's squared. So the smallest x can ever be is 1. This thing is always going to be bigger and no smaller than 0. At the minimum, this is a 0. So for any other value of y, this will be bigger than 1. The fact that it is squared means there's a symmetry up and down. When y is squared, there's an up and down symmetry about this line. So here we go. Something like that. Okay? Parabola opening to the right, and we found out the vertex, so that's the good shape here. And it's bounded by x is equal to 5 on the right. Before we sketch that, let's find out where we intersect the x-axis here. So I know where to put my 5, to the left or to the right of that. I need some kind of better indication where that line is. So let's find the x-intercept first. And how do you find the x-intercept? Right, you said y equal to 0. So in this equation here, we get x is equal to 1 plus 4, right? So 5. So the x-intercept happened to be where we bounded on the right. Now we're taking this region to go about the x-axis. So we're going to revolve this parabolic shape around the x-axis. All right, let me attempt to sketch the final solid we get out of it. Well, the outer shape is easy to sketch. And what's inside here? Something like that, right? See that? Can you visualize what this shape looks like? It has a little thing hollowed out. Okay? Set up your rectangle parallel to the axis of revolution. We're going around the x-axis. I have to set this up horizontally. All right, so we get our 2 pi. Next step is radius. What's my radius this time? How do you measure radius? From the axis of revolution to the rectangle. So from here to here. That vertical distance is y, right? Make sense? Okay, then the height, we're going to have to look at this rectangle kind of like that to determine the height. So how tall is it? Right minus left. 5 minus this guy right here. One, two, three. 1, 2, 3. Yep. Okay, 2 pi radius, height. So let me write these down. And I'll put height in quote because our rectangle is lying on its side. Thickness, dy, excellent. Okay, entire thing. Now we integrate. What are my integration limits? We're integrating in y, so we start at the bottom of the region to the top of the region. So 0 to, we need to figure that out, right? So what is this? This other one, this is when x is equal to 5. When we plug that into here, so y is equal to 0, y is equal to 4. So these are the two points where intersection happens. 0 to 4, 2 pi y, and then this thing here, 5 minus 1, that's a 4. Let's just do that right now. Minus the quantity of y minus 2 squared, dy. Next step, let's FOIL that out, simplify, distribute the y into here, and then integrate term by term. All right, so what do we have? We have 4 minus the quantity of y squared minus 4y plus 4 dy what's that? Are we having trouble with this 4 here? This number 4? Okay. Five minus 1, that's my 4, and then negative blah squared. Yeah? And then I took care of the blah here. Okay. That 2y is getting in the way. Let's get it out. And then simplify this a little bit. 4 minus 4, so that constant went away. Minus y squared plus 4y dy. And by the time we got here, we should be good. Okay, in the interest of time, trust me, the answer turns out to be 128 pi over 3. Okay, I got one more example. This time we're going to rotate this shape not about the x or y axis, but about some arbitrary line, vertical or horizontal, that we want. So we probably only have time to set this up. Region is bounded by y is equal to x squared. Y is 8 minus x squared. And we're revolving this to go about x is equal to 2. All right, so these are simple shapes. Y is equal to x squared. 8 minus x squared. Same thing, but pointing down has a vertex at y is equal to 8. The intersection points are relevant. Okay, so we set x squared to be 8 minus x squared. So 2x squared is equal to 8. X squared is equal to 4. X is minus 2 and 2. Okay, then x equal to 2. There's a bug flying here. So that's the line we want to go about. All right, so then, as usual, using the shell method, we have to set up the rectangle that's parallel to that red line I just sketched. And then we calculate the volume of one shell. 2 pi. Okay, so the most tricky part about this is the radius now. We got to be careful with our radius. Radius is always measured from this axis of revolution to the rectangle. So this right here, this is my radius. Not from the y-axis, because we're not going about the y-axis. So how would you write the radius as? And how did we get that? Yeah, the distance from the y-axis to the rectangle is x, right? The distance from the y-axis to 2 is 2. So the difference between the two is what I want here. So that's my 2 minus x. See that? From the axis of revolution to the rectangle. The height is relatively easy. What's the height? Top minus the bottom, so 8 minus x squared minus x squared. And then the thickness, dx. Then the entire thing, we integrate from where to where? Good. 2 pi times all of that stuff. 8 minus 2x squared. FOIL this out, simplify, and then integrate term by term.